This is lecture 21. So in last lecture we have discussed that Bode plot, and if we have some factor like s plus a or 1 by s plus a, we have already seen that what would be that asymptotic Bode plot. So today we will see the other factors. So first let us see that if we have that factor like s, so what would be that Bode plot? What would be the Bode plot whenever Bode plot for GS equal to S? So the first step is that GJ omega, because that is at steady state, so that would be J omega. Now if we take it in dB scale, so what we get, that is 20 log of GJ omega. So 20 log GJ omega, so that is, it would be 20 log of omega. So in dB scale, as we have discussed, so that means this is that magnitude in dB scale, and you can see that if this is y and this is x, so that would be actually y equal to 20x. So the slope that you would have, so in dB, in decibel, that slope that you would have, that is 20 dB per decade. So slope is 20 dB per decade. And what would be that value whenever omega equal to 1? When omega equal to 1 rad per second, then we can see that the value would be 20 log GJ omega, that is equal to 0. And what would be that angle? So this angle is GJ omega, that is equal to tan inverse, that is infinite, so that is 90 degree. So that means whenever we have a factor like S, so that angle remains constant, that is 90 degree, and that slope that we would have, that is 20 dB per decade. So in last class, here there should not be any minus, so that was a mistake. So that is omega equal to A, so that angle would be minus 45 degree. So here. So this is that Bode plot whenever we have S. So let us see what happens whenever we have the factor that is 1 by S. So that is Bode plot. That is that asymptotic approximation of the gain and phase plot. So Bode plot for GS equal to 1 by S. So in this case, what would be the magnitude and phase plot? So that is G J omega, that is 1 by J omega. So then it can be written as 1 by omega, and as that J omega in denominator, so the angle will be minus 90 degree. So in dB scale, that is 20 log GJ omega mod of that GJ omega. So then that would be 20 log 1 by omega, and it would be minus 20 log of omega. So again, in dB scale, we can see that this is y and this is x. So it would be actually negative slope with minus 20 dB per decade. So the slope is minus 20 dB per decade. So it is just similar to that s, but whenever there is 1 by s, that slope is minus 20 dB per decade. And what would be that angle? That angle would be constant, that is minus 90 degree. So far we have discussed, that means how many, so there are different factors, like whenever we have s plus a, we have seen that s plus a, we have seen that whenever frequency is small, then that gain would be 20 log a, and it remains constant up to 0.82 a, that corner frequency. And when frequency is high, that means at high frequency range, that slope would be 20 dB per decade. And it is just opposite in case of 1 by s plus a. So from 0.01 to a, that means corner frequency, the gain would be minus 20 log a here, and at high frequency that slope would be negative, that is minus 20 dB per decade. The same thing happens in case of s and 1 by s. Whenever we have s, we have seen that slope would be 20 dB per decade, but the phase remains constant, that is 90 degree. And in case of 1 by s, here the phase would be minus 90 degree and the slope would be minus 20 dB per decade. So let us see, whenever we have a factor, that is that second order factor, so then what would be that Bode plot? So what is the Bode plot for a second order factor, that is gs, equal to that s square plus twice zeta omega n s and omega n square. And here that omega n square, omega n is the natural frequency, and that zeta, that is the damping ratio. So let us see what would be that asymptotic Bode plot for this particular factor. So then we can write this gs, whenever we take that omega n square common, so then we have that s square by omega n square plus twice zeta s by omega n plus 1. So at low frequency, we can see that, so this particular thing would be equal to 0 and this is 0. So basically it would be omega n square. So it is approximately equal to that omega n square, that is gs approximately omega n square. So we can write that this is omega n square angle 0 degree. So in dB scale, that would be 20 log gj omega, whenever this factor is that second order factor gj omega. So this one would be equal to 20 log omega n square. And we can see that what happens in case of high frequency. So at high frequency, so at high frequency we can see that it is Gj omega. So Gj omega, that is, it is just S square. So that means it would be nearly approximately equal. So this is approximately equal to that S square, and that means that is, so we can write that this is Gs. So Gs approximately equal to S square at high frequency, and then Gj omega. So Gj omega, that would be approximately that minus omega square. Then we can write it in phasor form, that is omega square, and angle is 180 degree. And in dB scale, so that is 20 log Gj omega, that one would be equal to 20 log omega square. That means this magnitude only, this magnitude, and this one equal to, we can write, that is 40 log omega. And it is interesting to see that if this is that y, that is in dB, and this is that x, so the slope is actually 40 dB per decade. So that means it is the slope here, the slope equal to 40 dB per decade. So in case of that first order factor, we have seen that slope becomes that 20 dB per decade, but here the slope is 40 dB per decade. And what would be the value whenever omega equal to omega n? Because you can see here that whenever that omega equal to omega n, that is the natural frequency, then what would be its value? When omega equal to omega n, so that is omega by omega n equal to 1. So low and high frequency, so we can see that, so this is that high frequency one, so this is high frequency, that would be omega n square. And in this case also we can see in the low frequency, Gs equal to omega n square. So that means when omega equal to omega n, so then the high frequency asymptote and low frequency asymptote, they are same. So that means here we can write that low and high frequency asymptotes, low and high frequency asymptotes are same. So whenever you have one second order factor like this, so then the corner frequency, as the low and high frequency asymptotes are same, so omega n is that corner frequency. omega n is the corner frequency. So similarly, that means you can see here, that means whenever it is S, so at omega equal to 1, you can see it is becomes 0, and whenever S plus A or 1 by S plus A, so we can see here that is whenever S plus A, we have that factor 1 by S plus A, then the low frequency, that means this is at high frequency, the value is that omega, and that low frequency you can see that it is coming 20 log A. So at omega equal to omega A, we can see that low and high frequency asymptotes are same. So that's why omega equal to A in this particular case, that is that corner frequency. And what happens in case of second order factor, we find that omega n is the corner frequency. We can also represent this particular second order factor in normalized and normalized form. So let us see how we can represent it in normalized form, that is normalized and scaling. So normalized and scaling. So we have that factor, that is g of s equal to that s square plus twice zeta omega n s plus omega n square. So now we can write it, that means if we take that omega n squares common, so it would be a square plus omega n square plus twice zeta s by omega n plus 1. We can write this one as g of s1 divided by omega n square equal to s1 square plus twice zeta s1 plus 1, where s1 equal to s by omega n. So here what we have done, so this is actually that scaling, and here we have that taken normalized form. So now if we take that 20 log of this one, so then in the low frequency the asymptotes is 0 dB and the corner frequency is 1 rad per second. So let us write this one. So low frequency asymptotes is 0 dB. So in previous case what happens, the low frequency asymptotes was that 20 log omega n square. So now if we divide by omega n square, so basically that would be 20 log 1, so that would be 0. Here we have divided by that omega n square and we are taking that whole thing and 20 log of that one. So then that low frequency asymptotes is 0 dB and corner frequency what we are getting, that is in for this particular case the corner frequency is coming 1. So corner frequency is 1, and you can see that corner frequency is 1 means whenever s1 equal to 1, so s equal to omega n, and it is matching with this one, so omega n is that corner frequency. So that means if we have a second order factor, we can also represent in this form, and now if we divide that one with omega n square and if we define that s1 equal to s by omega n, so this is actually that scaling and this is that normalization, then we have that asymptotes, and this asymptote is 0 in the low frequency range and the corner frequency is 1. So this is actually the second order factor which can be represented in normalized and in scaling form. So now let us see what happens if we calculate that angle. So that gj omega, that is, it would be that minus omega square plus j twice zeta omega n into omega plus 1. So sorry, that would be omega n square, that is omega n square, because we can see here if you have this factor, so in place of s you replace j omega. So first one is minus omega n square, this one is minus omega n square, this one, and here j omega and omega n square would be there. So we have that factor, this one. So now if we rearrange this one, so we have that omega n square minus omega square plus j twice zeta omega n omega. So the angle that we have, because in case of second order systems already we have seen that angle that we are getting, that is 180 degree when it is at high frequency, so it goes to 180 degree. And here we are just trying to find, that means if we just replace gj omega, so what is that exact angle? That angle we have that tan inverse twice zeta omega n omega divided by omega n square minus omega square. So now this is that angle. So at omega equal to omega n, what we have, because that is that corner frequency. So at omega equal to omega n, that means at corner frequency, we have that angle, that is gj omega, that would be equal to 90 degree. And if we just look into this particular expression, then we can see that, so this angle actually affected by that factor, which is that zeta, that means that damping ratio. So we can actually see, that means this particular angle also varies with that zeta, that means whenever zeta is different, this angle also would be the different. And what would be that gain? Because the gain, if you find that gain gj omega, so that gain would be that square. From here we can find that omega n square minus omega square whole square plus twice zeta omega n omega whole square. So here also we can see that, so if we consider that corner frequency, say omega equal to omega n, so then what would be that magnitude? That is 20 log gj omega, this one. So if we take 20 log, so this term would be equal to 0, because that omega equal to omega n square. And now if you replace this omega by omega n square, so we would have that 20 log twice zeta omega n square. So here also we can see that at omega equal to omega n, so this particular magnitude depends on that zeta. So that means if zeta is different and that zeta is the damping ratio, then the gain also will be the different. So this, we can say that this difference depends on zeta. So what we have discussed here, so that means if we have a second order factor, so this one, so then we can represent it in this form, and we can see that at low frequency it is coming 20 log omega n square. So that is actually that asymptotic gain, and at high frequency we have that 20 log omega square, that is 40 into omega. So that means that slope would be 40 dB per decade. In case of S plus A, it is 20 dB per decade. So here the slope is double, and we can see that angle is 180 degree at high frequency. And then also we have shown that omega n is the corner frequency, because at omega n the low frequency and high frequency asymptotes are same. And now also we can represent it in normalized and scaling form that we have shown. So if we represent in that form, so then we have shown that the low frequency asymptotes is 0 dB and the corner frequency is 1. So now we are actually discussing what would be the exact angle and magnitude. So if we find out that exact angle, so that angle comes in that form and the magnitude becomes this one. So in both cases we have seen that they depend on the zeta value, that is the damping ratio, and particularly here we have found that at omega equal to omega n, that means at corner frequency, what would be the value of that gain. So that value is 20 log 2 zeta omega n square, and here again it is function of zeta. So that means if the damping ratio varies, so at corner frequency it would be the different. That means that magnitude as well as phase would be different. So here we can just show what would be the Bode plot of, say, suppose the Bode plot for GS. So here we can see that we have a second order so if we have a term, the second order term which is in the denominator, so then what happens? So here actually I want to correct one thing, that means at omega equal to omega n, so when omega equal to omega n, we can see that it becomes always 0. So whenever it becomes always 0, that means at omega equal to omega n, that angle does not depend on this zeta. It does not depend on zeta because it is becoming always 90 degree. At omega equal to omega n, it becomes always 90 degree. So it does not depend on zeta. But what happens? Only the magnitude, that magnitude actually depends on that zeta. So repeating, that means whenever we have a second order factor, at omega equal to omega n, that angle becomes always 90 degree, but we can see that the gain is different because it depends on that zeta. But what happens in case of phase as well as in case of gain, whenever we move from that corner frequency, then what would be that exact value of gain and phase? It depends on zeta, both gain and phase. But at omega equal to omega n, phase is always 90 degree. It does not depend on zeta, but gain depends on zeta. So now let us see what happens if we have a factor second order factor which is in the denominator. So it would be just reverse as we have seen for other cases. So that means that slope whenever that second order factor in the numerator, the slope was 40 dB per decade. So here that slope would be actually minus 40 dB per decade, minus 40 dB per decade. And that angle would be minus 180 degree. So in that case it was 180 degree. So here that slope of that angle slope is minus 90 degree per decade. So we can see here, that means in case of, so let us see what we have seen. So we are just trying to understand what would be the asymptotic approximation, that is that Bode plot, gain and phase. And then we have seen that whenever the transfer function, that is that loop transfer function, is given in this particular pole zero form, and if we take the magnitude, that means log, so then we have seen that these are actually the sum of all the gains, that means that gain and zero terms minus all the pole terms. So now we are just trying to understand that if we have some factors like s plus a, so then what would be that asymptotes. So in low frequency that would be 20 log a, and at high frequency that is 20 dB per decade. And we have seen that here at high frequency that angle becomes 90 degree, and the slope of that angle would be 45 degree per decade. Here we can see that is at 45 degree at corner frequency, so that slope would be 45 degree per decade. And in case of 1 by s plus a, the slope would be just reverse, that means it would be minus 20 dB per decade, and that angle slope would be minus 45 degree per decade. And what happens in case of that s, the slope would be 20 dB per decade, and for 1 by s it would be minus 20 dB per decade, but in this case that angle would be 90 degree, and here that angle would be minus 90 degree. And in case of second order factor, we have seen that slope would be doubled, it would be 40 dB per decade, and if it goes to the denominator it would be minus 40 dB per decade. At that angle would be at high frequency 180 degree with the slope 90 degree per decade, and whenever it goes to the denominator, so that slope would be minus 90 degree per decade, and the slope is minus 40 dB per decade. So just applying those concepts, so we can easily draw the asymptotic Bode plot for a given transfer function. So let us see. So first we draw some Bode plot, and we have taken so some examples. So here that first example is, suppose we have one factor which is s plus 2. So the factor is s plus 2. That factor is s plus 2. So then what would be its Bode plot? So as we know that we need to represent it. So here a equal to, so this is actually that factor, and here this is that a, and we can represent it as 2 s by 2 plus 1. So now what would be gj omega? So gj omega, that is equal to that 2 into j omega divided by 2 plus 1. And we can see that the first one, that is s plus a, here in the low frequency, so a is that corner frequency, and up to a, so 0.1 a to a, so we can see that it is 20 log A. So here A equal to 2, so that is 20 log 2, and 20 log 2 is nearly equal to 6 dB. So then if we plot that one, then what we get? So we are just drawing that asymptotic Bode plot, and here we have that this is log omega. So here rad per second, and here we have in dB. So the frequency, that means as it is in log scale, so that is 0.1, then 1, then 10, then 100, like that. So as we know that the corner frequency is 2, so this is suppose 2 corner frequency, and this is in log scale, and 20 log 2, that means in low frequency. So one factor would be that 20. So if we take that mod of this one, so that means 20 log of this thing, say 20 log of that. So then what we would get, that one line we would get, that is 6 dB. So this value is actually 20 log 2, and the corner frequency is here, because for this particular term the asymptotes is as follows. So from 0.1 to 2 it remains 0, and here there would be a slope, that is this slope is 20 dB per decade. So do not forget to write these slopes and corner frequency. So now if we take say 20 log of Gj omega, what we get? We will get that 20 log 2 plus 20 log of this particular factor, that is j omega by 2 plus 1. And for this particular term, already we have discussed, that means what would be that asymptote. So this one is that asymptotes, and this is that value, so this is that value. So what would be the Bode plot? The asymptotic Bode plot is this one, comes here, and so this is that asymptotic Bode plot, and here this is in dB. 2 is that corner frequency. And what would be that phase plot? So if we draw that phase plot, so here we can see again that would be in log scale, log omega. So then those frequencies are 0.1, and here we have that 1, then 10, so 10, 100, like that. And we have seen that in case of S plus A, whenever the frequency is high, the value it would be, that is in degree, so it is at plus 90 degree. So plus 90 degree means here, and we can see that what is that corner frequency? The corner frequency is 2. Here the corner frequency is 2, and we know that, so at corner frequency the value is 45 degree. The value is 45 degree at corner frequency. So the point is here, that means this is that 45 degree. So now as we have seen, the slope is 90 degree, that is the 45 degree per decade. Whenever you have a factor s plus a, we have seen here, let us see once again. So whenever we have that s plus a, we have seen that at high frequency it would be 90 degree, and the slope, so at omega equal to, at omega, when frequency equal to that a, that means in that case omega equal to 2, the angle is 45 degree, and the slope is actually 45 degree per decade. So whenever we draw the phase, so we take one point here, that is 1 decade below to this corner frequency and 1 decade above that corner frequency. So here, then this is that slope, and this is actually that phase plot, asymptotic phase plot, and here you should write that it is 40 degree per decade. So this is that slope. So in this particular example, what we have seen, whenever we have a factor s plus 2, what would be that asymptotic Bode plot? And we can find that this is that gain plot in dB, and 2 is that 2 is actually the corner frequency, and we can see that phase plot at omega equal to 2, that is that corner frequency, that angle equal to 45 degree, and whenever omega is high, so this angle is 90 degree, we have shown here, and this slope is 45 degree per decade. So let us see, whenever we take, these are actually not example, we have already discussed it, we are showing that what would be its plot. So that means whenever you have 1 by s plus a, so suppose gs, you have that 1 by s plus a, and we have shown that what would be its Bode plot. So asymptotic Bode plot is here, so this is that log omega, and this is in dB, so do not forget to mention that axis, and you can see that the frequency is 0.1, then 1, 10, 100, like that. So if a is that corner frequency, suppose this is that a, so this is that a, and we have seen that there would be one gain, so this gain would be 20 log of 1 by a, so that is minus 20 log a, so that would be that constant gain, and the asymptotes for that 1 by s plus a, that means 1 by s by a plus 1, so that asymptote would be like this, it would be in the negative side, and this slope would be minus 20 dB per decade. So what would be that plot? So basically it would be up to this, and then the slope is minus 20 dB per decade. So this is that asymptotic Bode plot, that is that gain. And what would be the phase? So the phase plot is, so this is that log omega, and here that is degree, and we have shown that when omega is large, that means at high frequency, so that angle would be minus 90 degree, and at omega equal to a, that means at corner frequency, so at corner frequency This is that corner frequency we have taken. So this is that A, and we have shown that at corner frequency the value becomes minus 45 degree. So similar to S plus A, we know that. So take a point that is 1 decade above and 1 decade below, and here we know that this slope is minus 45 degree per decade. So this slope would be minus 45 degree per decade, and when omega is high, so then that angle is minus 90 degree. So whenever we draw that asymptotic Bode plot, do not forget to mention that axis, then do not forget to mention that corner frequency as well as that slope, this gain, and here also this slope. So let us see, whenever we just plot S or 1 by S, then what would be that plot, asymptotic Bode plot. So let us see. So this is that frequency, that log omega, and here you have that is in dB, and we can see that the angles is up, the frequency that is 0.1, and say here this is 1, this is 10, like that. And we know whenever we have that S, the slope is 20 dB per decade, and it crosses that 0 dB line whenever omega equal to 1. So this is the 0 dB line, and we can see that at omega equal to 1 it crosses that 0 dB line. So this slope is 20 dB per decade, 20 dB per decade. So this is that plot of S. Then what would be the plot of 1 by S? So plot of 1 by S, it would be just with the negative slope, this one. So this is that plot of 1 by S, and here the slope is minus 20 dB per decade, minus 20 dB per decade, and at frequency omega equal to 1, it crosses that 0 dB line. So let us see what would be that angle. So this is that log of omega, and here we have that degree. So in case of S, we have seen that angle would be 90 degree. So it remains constant all through the frequency. So this is 90 degree. So this is 90 degree. So this is that plot for S, and for 1 by S, that is that plot for 1 by S, and here the angle is minus 90 degree. So these are the plots of that individual factors we have shown. These all are the asymptotic Bode plots. Now let us see, suppose one transfer function is given. Suppose one transfer function is given. So that one is, suppose the transfer function, we take one example, that is GS. So G of S equal to S plus 3 divided by S plus S plus 1 by S plus 2. So suppose this is that open loop transfer function or loop transfer function is given, and you are asked to draw what would be the asymptotic Bode plot. So there are 4 factors. We can see there are 4 factors. So the first step is you just represent it in this form. So if you take that 3 common here, and in this case if you take 2 common, so that would be s plus 3 plus 1, and here you have that s, then s plus 1, and here you have s by 2 plus 1. So then we can just apply the concept that you have learned, that what would be the Bode plot here. So here first we draw that magnitude plot. So this is that log of that omega, and so this is that point 0.1, then you have that 1, 10, 100. So the first one is, if you look at here, so this is that gain, so that means one gain you would have, that is 20 log of, so you have, so this is in dB, so one factor that you would have, that is 20 log 3 by 2. So 20 log 3 by 2, it is coming say nearly equal to 3.52 dB. So that means one line would be there which is like this, that is that 20 log 3 by 2. So then if we consider this factor, that is in numerator, and you can see that corner frequency is coming. So suppose here this is 2 and this is 3, so they all are in logarithmic scale. So I am just showing that corner frequency, but they are not in proper scale. So now the corner frequency is 3 and it is in the numerator, so that means that asymptotes for this particular term is coming like this, and from here we have that 20 dB per decade. So this one is coming, that is 20 dB per decade, 20 dB per decade here, and this is that factor, that is s by 3 plus 1. So now for this factor, or first we say that this factor, say s, and for s there would be a slope as that is in the denominator. So this is that slope, that is minus 20 dB. So this is for s, the slope is minus 20 dB per decade. So now for s plus 1, we can see that s plus 1, so that means again we have a slope here, we have a slope that is, which is just overlapping, and here corner frequency is 1, that means it will be overlapped with this particular one, that is, so here I am writing that is that s plus 1. So this portion is overlapped with that, so I am just taking another color. So this one, it is overlapped with that s, and this slope is, so this one is s plus 1, s plus 1, that is in the denominator, and we have another one, that is s by 2 plus 1. So s by 2 plus 1 means up to this, and here we have another one, so that is again that slope is minus 20 dB per decade, and this is that factor, that is s by 2 plus 1. So now if we just add those terms, so how it would be, so we can see that because of this particular term, that is 20 log 3 by 2, So this one would be shifted. So this one would be shifted like that, and it will continue up to that. So then we can see that here, if we just use that black, it comes here. Then here you have two slopes, that is -20 and -20, so -40 dB. So from here to 2 we have that double slope, and this slope is coming -40 dB per decade. Again, I am explaining why. The reason is, if you look at this particular portion, you can see that there are two slopes. So for S and for S plus 1. So that is -20, -20. So -40 dB per decade. And then we can see that from this particular, so this is the 2 point, 2 and 3, there is another slope. So that means from 2 and 3, this slope would be equal to, so this slope is equal to -60 dB per decade. -60 dB per decade. The reason is, here you have S and S plus 1, that is -40, and again for this particular point here there is another slope -20, so -60 dB per decade. And you can see here the plot, it is very difficult to understand that it is -40 or -60. So whenever you draw that asymptotic Bode plot, you should not forget to mention what is that slope. So here that slope is -20 dB per decade. And at 3 you can see that there is one asymptote which is with positive, so, and it is 20 dB. So from -60 plus 20, so that means you have 40 dB, -40 dB per decade. So that means from here you have a slope that is say -40 dB per decade. So this is that asymptotic Bode plot. So here you have that -40 dB, -40 dB per decade. So this is that asymptotic Bode plot for this particular transfer function. So this is that gain for this one, and for that first factor in the numerator we have this one. And what we have done, for each factors we have drawn separately, then we have added it, and that slope is very clear because if you first locate those corner frequencies and if you just add those things, so accordingly you can find what would be that slopes. So here that would be -40 dB per decade. So up to 2 here, and from 2 to 3 it would be -60 dB per decade. And after that, that means after 3 it would be again -40 dB per decade. So that slope and this slope, they will be same, but in picture they are different. It looks different clearly, but so that's why I have pointed out that this is -40 dB per decade and -40 dB per decade. If we can draw it perfectly, so then that is fine. Otherwise there is no problem if you mention that this is that slope with -40 dB per decade. So now let us see what happens in case of that phase. So this is that degree, and we can see that what would be the phase. So here again that phase, we can see what would be that corner frequency. So here that 0.1, then we have that 1, then 10, like that. So here we have one corner frequency, that is 2. We have another corner frequency, that is 3. And for S, we have seen that for S it is, so this is 0.1, this is 0.1. So for S that angle is minus 90 degree. So the angle is, this is minus 90 degree. Now what happens in case of this S by 3 plus 1? So at 3 we can see that at 3 we have that minus 45 degree. So minus 45 degree here, and that would be that 90 degree. So here the angle is like this, so it goes like that. So that means at the corner frequency, here, that would be plus 45 degree, and we can see that one decade below this and one decade above that. So the slope would be here, the slope is 45 degree per decade. This is for that first term. So we have done it for first term and S term. So this term and that term we have done. So then for S plus 1, we can see that at 1 it would be 45 degree. So that means there would be one, so here that is 1, at 1 it is 45 degree. So that would be like this. So this slope is minus 45 degree per decade, and here we can see at 1 it would be minus 45 degree. Similarly for the second one, we can see that at S equal to 2, it would be 45 degree. So that means S equal to 2, there will be a shift here and you have this one. So that means at S equal to 2, this angle would be minus 45 degree. So now if we add those things, so what will you get? We can see that it starts from 90 degree and up to this there will be a slope, and then from here to here, because here that would be 0.3, 0.3, here that would be 0.3. So then 0.2 to 0.3, the slope is actually minus 90 degree. So here the slope is minus 45 degree, and here slope is minus 90 degree, because you can see here this is one slope and there is another slope. And then after 0.3 there is a positive slope plus 45 degree. So that means there would be the slope which is minus 45 degree, again minus 45 degree, and it would continue like that. And then if you just add it, and finally it goes to minus 180 degree. So that is that minus 180 degree, and from here actually clear, that means in this transfer function, from this transfer function you can see that for at high frequency this will contribute 90 degree and this one contribute minus 90 degree. So this one is 90. So minus 90 means minus 180 degree. So that means at high frequency it will go to minus 180 degree. So do not forget to mention that slope. So here in the angle what we have done, so that means we have individually plotted those slopes, and then we found that the slope will go like this. So initially it would be minus 45 degree, and after that minus 90 degree, because these two slopes will be added, and after that there will be a positive slope. So then again minus 45 degree, and finally it goes to minus 180 degree. And so these frequencies from this plot, it is actually, you can do it very clearly, because it starts from 0.1 to 10. Then the second one, it comes to 10 point, that is 1, so that is it ends at 11. And then the third one 0.3, it ends at 13. So accordingly you can find that what would be slope, and finally at what point it comes to minus 180 degree. It can be done easily. So let us see what we have discussed today. So today we have actually started with that S and 1 by S and 1 by S, and then we have discussed on the second order term, and then we have shown, that means if we draw the asymptotic Bode plot for S plus A, or 1 by S plus A, or S or 1 by S, then how it looks like. And we have taken one example, and this transfer function is that loop transfer function. So whenever a loop transfer function is given, how to draw that asymptotic Bode plot we have discussed here. So first you draw that individual component and then take a sum, and this is that phase plot. And do not forget to mention that slope as well as that corner frequency. So in the next class, in the next lecture, I'll be showing that how to plot that second order terms. We have already discussed, that means what would be those values in the low frequency and high frequency, and at corner frequency omega n, what would be the value, and that how the gain depends on that zeta we have already discussed. So in next class we will be just solving one problem, and then we will just complete that Bode plot. Thank you.